We've all been there, in the middle of a job, everything going smoothly, until boom, you're missing a part. United Refrigeration is your one-stop shop for all your refrigeration needs. Use your computer or smartphone to go to www.uri.com at any time of day or night to check stock on your favorite brands, such as Copeland, Sporlan, Carlisle compressors, Danfoss, Emerson CPC boards and sensors, Carrel, Hussmann parts, and Co2. United Refrigeration Inc. is home to these brands and many more. Looking for information on refrigerant conversions or refrigerant banking? Quick access links on the homepage can get you to the information you need. All approved accounts are able to see live to-the-minute inventory and pricing. Product not in stock at your local branch? No problem. Use the Nearby Stock feature to find a local branch that does have what you need. Are you looking for a branch address, phone number, or after-hours number? That's all available as well. Just click on the branch locator and search for your local branch. Have a model number and looking for a replacement part? www.uri.com/ARP has a vast list of quick pick replacement parts. Just search for the model number of the equipment you're working on and click the Replacement Parts tab. If you don't have an account, click the Register button and we'll have you online in no time. With more than 400 locations in North America, each United Refrigeration branch is fully stocked for immediate pickup. Our branch employees have in-depth technical knowledge, so we can help you get what you need when you need it. Visit your local store or www.uri.com/ARP today. United Refrigeration Inc. has all your solutions down cold.
The Sporlan division of Parker Hannifin Corporation is sponsoring this podcast. Sporlan is the leading manufacturer of HVAC&R components. Using quality materials and craftsmanship, Sporlan maintains a commitment to innovation, manufacturing excellence, service, and support for its customers since 1934. The company is known for its catch-all filter dryers, thermostatic expansion valves, solenoid valves, pressure regulating valves, suction filters, electric valves, controllers, supermarket monitoring solutions, chemicals, smart service tools, ZoomLock Max, Press to Connect, and ZoomLock Push, Push to Connect refrigerant fittings. If folks want to learn more, what do they do?
You can go to sporlan.com.
I guess that's Jim and John for Sporlan signing off.
Good evening, everybody, and welcome to Advanced Refrigeration Podcast. You're here with your host, Brett Wetzel and Kevin Compass. What's going on this week, man? You busy?
Kind of, sort of. Kind of like a slow week. Change condensers again. Like, I think we're on like condenser number like 200.
Yeah, you've been doing a lot of those. Kev, you were pre-piping all those. Are you still doing that or what?
Yeah, the fitters are pre-piping them. I think this is the last one going in for a little while. I think we did like, I don't know, like 30 or 40 stores. There was like 3 or 4 or 2 or 3 crews going like nonstop, doing a store a week.
Gotcha. Nothing bad. I'm expecting something to drop.
No. I only got one more work day, and then I'm on like a mini vacation the rest of the week. So
going anywhere cool?
No, I'm just going camping. So
tomorrow's butcher day.
Tomorrow's Friday. Yes.
I say that because every Friday when I talk to him when he's going out camping, he's like, he usually is on the phone with me when he's at the butcher shop, and it's usually 11 jalapeno sausages, and I almost know your whole order to stock. But hey, tonight we're talking to Wynand Groenewald, which he told me Bob because I didn't want to keep butchering his beautiful Dutch name. So I'd like to introduce Wynand. Hey, what's going on, man?
Well, good. Thanks for having me. Yeah, can't complain. Keeping busy.
Awesome. We Kevin and I met Wynand down at AHR down in Georgia. And it was that conversation that we said that we had with Andre and him, and I think we were literally talking for like 2.5 hours just about random stuff, and it was all really good stuff, but we didn't record anything. So I said to him, I was like, hey, we're gonna hook back up and talk about some of the stuff that we were talking about at AHR. But man, if you want to introduce yourself, tell everybody a little bit about yourself, what you've been working on, who you work for, and all that other fun stuff.
Sure. Cool. Yeah. So, I mean, the reason why I'm here is CO2. That's kind of my passion. That's what I entered this industry on. So currently I'm working for a company, FGN, which myself and my partner founded about 2.5 years ago. Before that, we both worked together. Actually, before that, for about 15 odd years, we were in a company which I said gave us a lot of experience. We came from a background where we designed, manufactured, installed, service, took care everything around CO2 systems. So our first CO2 system we did about 18 odd years ago. So that's where we got a lot of experience, like hands-on, which I think makes us a bit different from the standard consulting company out there. Is we can not just consult on the theory and the practice, but we can actually consult on the physical side of life and how to put these things together and how to make it done. So part of what we do is we help product development. So we help a few OEMs across the globe to put products together, move away from HFC-based chillers, heat pumps, refrigeration-based systems, and we actually help design these systems, put it together, help them manufacture it, help them train up their guys and get it into the field. And then also quite a bit on the industrial side of life. So we do a lot of work for Maersk, where we put up a lot of cold storage facilities, nice challenges because the whole net zero goals that they have and large companies like that. So basically we try to take, we're not allowed to have any other refrigerant, no matter how small the capacities are on site. So basically we drive everything from the main plant or look for alternatives where we can recycle, reuse. So a lot of nice challenges. So we're based in South Africa, small team, but quite busy. We work all around. Currently we've got projects going on in New Zealand, Saudi, Australia, Japan, Pakistan, Kenya, Italy, and Spain. Yeah, I was in Spain last week. So, and in the US as well. So, we actually just opened. I think last time we spoke, we said we were doing it. So we've opened a branch in the US now, and I'm currently filing paperwork and getting stuff ready to get myself and the family over there and see if we can help the market. I think, yeah, in a nutshell, basically we support CO2. So that's what we do. We would like to get guys. Our goal is to get CO2 into the market. The more people we help, the faster it goes. We always tease ourselves and say, like, if we do our job well, we continuously will work ourselves out of clients. But that's our goal. So our goal is we can, if we partner and help as many companies as possible, everything just goes so much faster.
Well, you know what, Kev, before you came on, we were talking and like I said, like every single time it seems like I talk to Wayne, like, or I talk to someone else and I'm like, oh yeah, they're telling me about some CO2 project they're doing. And then all of a sudden I talk to him and he's like, oh yeah, I helped with that. And then like he kept going, like every single time I bring up another project. Oh yeah, I did that too. So like apparently, like you do a lot of different jobs in a lot of different countries and a lot just all over the place.
You're the puppeteer in the background pulling all the strings.
Seriously.
We try to, like I said, I mean, we that's nice being in a consultative role. We can help more than one party. So that is nice. So we like to work with OEMs, contractors, end users. And again, because we're not just on the theoretical side nor on the practical side. We've got a bit of an array of everything going. So we can help whomever needs some help to go to CO2. Yeah, and have fun while we do it. So it's interesting stuff always. It's never boring.
That's awesome. So he's on here tonight. We're just going to talk about a bunch of different stuff that we have questions about. Kev, do you want to start with what you had first, and then we'll get into some of the other stuff?
Well, let's go into what you had first with the piping thing, because
right.
that literally just came up today. So,
right, so
Brett,
So I was talking to Wynand before, because I'm trying to build some training, and I want to make sure I have everything correct. And the problem I'm having is, some scope you look at the manufacturer, and for liquid piping, I mean the suction piping is typically always still the end. It's still the way it always is. Basically, you feed it into the top, right? Helps with boiling off some of that refrigerant that you might have liquid laying around, and just kind of atomizes that oil a little bit. But then with the liquid piping, most of the time we're all used to everything pulls off the bottom, everything, as far as the liquid. But then when I'm looking through a lot of the spec, I start seeing, okay, Kaiser's like, oh, I want to feed off the side. I think Zero Zone the same. I looked at some plans for 1 or 2 customers, and they're showing pull off the side. So I started asking those questions because I want to make sure I get it right. But I want to talk about this for a little bit and see what your thoughts are.
Yeah, so I mean, as we touched, I think predominantly our go-to is bottom for liquid, to be honest. I think, like we discussed on it, the side is not a problem. There's 2 factors that you need to consider when you look at the pipe sizing or piping of the system. Like we said, CO2 is fairly sensitive to pressure drop. The main reason being, no matter what subcooling you gain from your gas cooler outlet or condenser when you're in a subcritical mode, as soon as you expand through your high pressure valve, basically at a saturated liquid. So if you do not subcool, predominantly we'll see your refrigeration systems either have the flash gas going over the liquid, get some 2K or 3K subcooling out of it. A lot of times you get your superheat out of your LT coming back. Use that to subcool your liquid. So the main reason for that is to basically give you buying yourself a buffer, because if you're right on a saturated, any pressure drop is going to start flashing. So you're going to start getting your liquid flashing into vapor. So if you're going to pull up, the higher you pull up out of the pipe, obviously your vapor is sitting at the top. You're going to pull that vapor out with your liquid going to a certain case. I mean, that vapor needs to end up somewhere. So like we said, usually if you have that problem, you'll see it at end of line. Like you're either short of gas or you flashing too much, your pressure drops too high. You'll see it end of line. The second factor that you need to consider, what we said, is depends on the type of oil, but the same as your suction, it's your oil carry. So POE, highly miscible, and CO2 carries very well. So in your liquid side, that's not an issue. If you have bag in your system, your typical liquid temperature, your bag is going to be at the bottom. So you would like to feed that bag with. So that can be something that maybe that I can consider is, when we do look at bag, you might want to take out of the side so that you don't slug all your oil to the first case. So that can be a reason for side track. So it would be a good question to ask or to find out that where it is typically specified to take it out of the side, if that is a pack-based system or a POE-based system. If it's POE, I would say go out at bottom, make sure that the vapor heat, that last case, helps with fault finding. And a full bore of liquid is number one for an expansion, especially electronic expansion device.
So because of what you said, as far as the liquid being essentially a saturated liquid, where you don't really have much subcooling there at the bottom of the flash tank, you might get like we talked about 2 or 3 degrees Fahrenheit of actual subcooling on there. So that's what I originally thought. I thought maybe because it's a shittier quality of liquid, because we're essentially manipulating the CO2 to make it do what we want it to do, right? As far as out of the HPV, we understand that yes, in subcritical mode, we have like a 70-30 mix, 70% just about liquid, 30% vapor, and as we go to transcritical, it's more like a 50-50, somewhere in that range, right? But so if you had, that's why I'm assuming that's why a lot of manufacturers, typically use the suction of the low temp to typically additionally subcool the liquid either on the drain leg or, potentially, coming out of the actual out of the flash tank. So you get that additional subcooling. So you have a little bit better of a quality of liquid. Would that be an apt description?
Yeah, exactly. So, I mean, if you have anything that you can, it's a benefit. Firstly, you can reduce your required superheat at your evaporator. So it's two-sided win. I mean, if you can run a DX, if you run a DX system and you can reduce the superheat required at your compressor or at your evaporator, sorry, that's a benefit. You gain that superheat, number one, and number two, you gain that additional what you can call subcooling. So all that means is you're basically pulling yourself out of that saturated curve into the liquid side of life, meaning that if you have a half a bar or whatever pressure drop on your liquid line supply, you're not going to start flashing. You're giving yourself that buffer. And also, like, I mean, you're moving flash gas, so that's another thing that you need to understand. Like the flash gas in a system is actually very interesting. I mean, that comes back to the high ambient strategies. Like every high ambient strategy is based around taking care of the flash tank in the receiver. But one benefit, and it comes to the low side of life, is where CO2 really gets the benefit of having the flash tank, because we need to consider that flash tank is not a CO2, flash gas is not a CO2 thing, it's any refrigerant. As soon as you have a pressure drop and you go into your two-phase region, you separate vapor from liquid. So basically, with CO2, you do a lot of that in your high pressure, in your receiver tank or your separation vessel. But what that means is you're feeding a constant liquid to your evaporators. So from a design point, it actually supports the design of the evaporator. You can have a much better, your evaporators don't see ambient. So that's the main difference between an HFC system and a CO2 system. Is if you design a CO2 system, you design around making sure you've got the mass flow capacity, compressor capacity, to deal with your fluctuation in flash gas according to ambient conditions. HFC-based system, you need to design your evaporators to take care of your ambient conditions as well, because if your tank there goes higher and your condensing temperature is higher due to ambient, you're going to end up with that 30% flash gas or 40% flash gas entering your evaporator, where in the winter conditions you'll have your 10% entering your evaporator. In a CO2 system, because you have that separation vessel, you're constantly feeding the same pressure temperature to the evaporator. So that evaporator is 365, 24/7, seeing the same feed to it. So it makes a good operation on the evaporator side. But yeah, from a piping side of life, yeah, you want to try and reduce that, getting that vapor, and it's always interesting. Like you can hear it. I don't know if you walk through a facility or something or an installation in the beginning, especially if you have the Danfoss valves, which is the solenoid driven valves, like you can hear it. So if you hear those pulse valves, you can hear them click. You're still short on gas, then, or you've got vapor going through your expansion device. Yeah, if you hear them click, there's vapor. Otherwise, you shouldn't hear them click that easily.
No shit. I never realized that. Kev, is that a new thing for you too?
They get quieter when they're especially they even quiet down a lot more when there's more caseload. But yeah, in the beginning, when the superheat's kind of hunting, when the empty case, the superheat's kind of hunting all over the place. So yeah, that makes sense. But gotcha. I mean, the liquid piping, it's interesting. It's just I wonder if it's something with the U.S. manufacturers just not catching up to everything yet. I mean, it seemed like one manufacturer started doing it, then they all started doing it. They all just copied, and every spec looks the exact same.
Like the picture in the one customer prints looks exactly like what's in the Kaiser Warren book. Like it's the same damn picture, same orientation, same thing with the Husman shit. It's literally, I think, the same picture. So I think someone made it and they're like, yep, that's what they're doing. We're gonna do that across the board.
Yeah, same as Hill. If you look at Hill's picture and Zero's picture, it's the same exact thing. So I mean, somebody went across the board. I mean, me personally, I would rather see it off the bottom.
Yeah. Well, so I talked to Ray Kelly about this because before when I met up with him in California, we were talking about it, and the idea is that because it's a lower quality of liquid than what you typically get, right, and more susceptible to pressure drop, the idea is that if you evenly give a little bit of case, a little bit of flash gas, then it's not as bad as basically just having total vapor at the end. That was his thought, but I mean, now I'm thinking otherwise. So
yeah, I mean, my counter on that would be is I would not want to sacrifice little. I would not like to sacrifice 5 to 10% over, I don't know, 50 odd cases. I'd rather see one case completely suffer and know I got a problem that I need to fix, because then I can fix it. Otherwise, otherwise I give it up on all the other cases. It's going to be the same. It's just spread out and you don't realize it.
Okay. And since we're talking about piping, I just want to ask this question. I was reading through the pump liquid stuff and I saw, they're really careful with, putting like downsizing the cases so you still have even flow across everything. Is there any difference? Like, I mean, they don't want you to basically start from one end of the case and go to the end. They want you, for pump liquid, they want you to basically start from the middle and then keep going down every single case. Is that have you seen that in the past where they would rather do that, go off the middle and out rather than start from the end and feed in for the pump liquid? Or if you were to design it, well, how would you do it? Is really the question.
You mean like sorry, I'm just trying to understand the question. Like, you mean like the how you
distribute
to the different cabinets and stuff like that.
Yes,
So
yes.
not have a ring feed, but rather have a, like, try and split through the center.
Yes.
Nah.
See, we've always done first in, last out. So first case to get liquid in is the last case to get suction out, or the vapor return line out. So that way, the first case, just like we would pipe glycol, that's how we've done it. So whatever case gets fed first is the return line is the farthest away. So, I mean, I don't really think it does anything, just for the fact that, I mean, all those cases have solenoids on them. So, I mean, they're going to cycle on and off as needed if temperature. I mean, but most of the time that stuff just floats off the vessel.
Yeah, and I mean, and you've got your overfeed ratio that you connect to that. So, I mean, in my opinion, I agree with you, Kevin. Like, typically do it like the similar way. I don't think necessarily you have to do a different configuration than you would do with any other type of pump system. I mean, for me, the main thing with your pump type system is to ensure that you've got your liquid overfeed correct and that you work according to that. So I must say we've more done pump systems on industrial blast freezing applications.
Mm-hmm.
So it's not so many coils that you have a complete split, but it's more like I say, it's more that getting that overfeed ratio correct and making sure that your pump can handle the high volume and the how can I say it, the discrepancy in requirements according to load.
So I have a question now that you brought up the blast freezers. So like I did a little bit of industrial for a couple of years, and most of the stuff that was blast freezers that were filled with liquid. You had a vessel at the top that was fed off the pump liquid, and basically that cylinder, that receiver at the top would basically fill up based off of a Hansen rod, right? So it's trying to maintain that level in there. Typically, you have a hand expansion valve. Is that the same? Are you doing a lot of the same stuff with industrial liquid flooded evaporators as you would with CO2 versus ammonia?
I think a little bit less mechanically and more electronically, but similar concepts. Yeah, I would say similar concepts. So I mean, you basically, again, you got your vessel and you got your compressor, whether it's LT or whether it's empty. But let's say it's an LT application blast freezer, so you will have your high pressure, your medium temperature compressors act like the same way. You'll have a receiver tank, so you'll have your high pressure valve, flash tank valve, controlling that liquid will feed through so that would just be electronically and not mechanically. It would feed into a surge tank, so that would just feed straight into a surge tank, and the surge tank will circulate the CO2, and the vapor will be taken care of. The LT compressors will pull straight out of your surge tank.
Okay, so pump liquid out from the flash tank, right? With liquid feed, and then going to what you're calling the surge tank, which would be above the evaporator, right? And that's where the line basically feeds the liquid off the bottom. Vapor and mixed liquid come back on the top, then dumps back in there. So if you do have some liquid, it does drop out and be utilized, and then pulls the vapor off the top. So you have a dry vapor, dry suction coming back, right?
Yeah, exactly.
Okay. Perfect.
Yeah.
I'm all
Exactly
out of
that.
piping questions. So, Kev, you got anything else for piping before we roll to what you want to talk about?
No, I think that's good. Before we roll into the high ambient strategies, which seems to be like what everybody talks about, I want to talk more about low ambient strategies because I live in Chicago. So it's the complete opposite of where Brett lives. He lives in Satan's asshole, like all year round. It's miserable down there. We get down.
He's moving. I think he might be moving to Texas. Shut your mouth.
He'll be fine.
I've been there. I'm used to the heat. It's fine.
Yeah. See, the heat doesn't bother me. It's the -10, -15 with the wind chill, -30. So we get that up here. Now,
Yeah.
we have nonstop problems all winter long. The DX racks, just as long as they're set up right, they'll run. But the CO2 racks, for the most part, unless they have a decent amount of load, all crash. And it seems to be a couple customers where they have a little load and they have nightshades. We fight the fight back and forth, and we end up running out of variable speed compressor. Basically, we can't go down any farther, and hot gas injection just ain't cutting it. So
you got there's two problems with that. Like, contrary to the pressures that you work with CO2, the compression ratio over a CO2 compressor is actually low compared to other compressors.
Yep.
So that is one thing. If you then run into that low ambient conditions, and especially with optimized saturated suction temperature, your compression ratio becomes very low. The first thing that happens with that is you reduce your discharge pressure and your discharge temperature. Sorry, you reduce your discharge temperature quite a lot. And then what kind of happens is, because and in between that low pressure differential, you've got an intermediate vessel now. You've got your receiver tank trying to sit between your saturated suction temperature and your discharge.
Today's episode is sponsored by the Refrigeration RDP series differential pressure monitors from Westermeyer Industries, now available for transcritical CO2 systems in addition to other common pressures and refrigerants. When the filter element of your coalescing oil separator is contaminated, it can hurt your system's performance and efficiency. But how do you know when it's time to replace that filter? Wait too long to replace, and you could end up with a nasty filter blowout. But replacing too often can be a waste of time and money. The answer is installing a differential pressure monitor. The RDP series differential pressure monitors, including the new transcritical CO2 model, are available now from Westermeyer Industries. To find out more information, email sales@westermeyerin.com. That's WESTERMEYERIN.com.
Hey guys, today's episode is sponsored by Westermeyer Industries serviceable oil floats. Many oil separators contain an oil float to effectively meter separated oil back to the compressors. Westermeyer Industries has taken this concept and perfected it with their new line of serviceable oil floats. These floats feature an improved design with fewer components, allowing for greater manufacturer consistency and up to 20% increased oil flow versus their legacy models. These floats also feature an integrated magnet to shield the oil path from debris and have been field proven in supermarket applications. Westermeyer Industries offer replacement oil floats not only for their own separators, but also cross-compatible models for our competitor oil separators as well. You can find out more about the Westermeyer Industries serviceable oil floats by visiting westermeyerind.com/floats. Once again, that's westermeyerind.com/float. Let's get on with the episode.
Pressure. So what we found is, like, what we've seen it before, where we get what we call it silly season, where everything basically just gets pumped in the machine room. So you even see your compressors running flat out, but there's absolutely nothing happening at the evaporators. But your machine room is running hard, and it's because your flash gas flash bypass valve is just opening up, trying to do something, but it doesn't know exactly what to do. So the best high ambient low ambient strategy, because the problem that you have is, again, it's always everybody says I always take a problem to the benefits of CO2, but it is like the benefit of CO2 that you have is it's got very good heat transfer coefficient. It's got a high volumetric efficiency. So if you're at that low operating ambient conditions, your condenser essentially for that system is huge. Because the second thing that people do, and especially if I understand what will happen in Chicago, and that is one design issue that I have and I always fight, is everybody looks and design a refrigeration system for the
Worst case scenario.
Yep.
0.05% operating time of the year, which Chicago is 105 F. So people design that system at 105 F, which I don't agree with, because you've got adiabatic probably also there, but they still, what if the water cuts, and what if it's 105 F there, and all of that shit, which people believe CO2 don't work at those conditions. It works, it's just not efficient. But I'd rather have a bit of a less efficient system for 0.5% of the year than a less efficient system for 60% of the year. But anyway, that's a different topic. So, but basically, what happens is your gas cooler / condenser now is highly oversized. So any trickle of wind will make it over condense. So the best way is to basically, in those conditions, what I would say for extreme weather fluctuations, you need to bypass that gas cooler. You need to have the ability to bypass it. Floating the fans is not good enough. Switching the fans off is not good enough. You're still gonna take too much heat out of that, out of the CO2.
So it's two things I want to bring up. So, okay, because we have one manufacturer that tried that. That tried the and it's working. They're bypassing the gas cooler and injecting right into the flash tank, and it seems to be working. I mean, these racks have very little load. We float them to like we go from like running a plus 18 SST to like, I think one of them I'm running a plus 20 26. Yeah. But I mean, we hit that. We start hitting that threshold of where the flash tank's running a plus 33 or plus 34, and we don't have that pressure differential. Now, I was screwing around with a 326 one day, and I kind of fat fingered the max receiver set point, and I fat fingered it, and I was a few half a bar up higher than I should have been. Well, I ended up knocking the top receiver up to like 550, 560. And it opened up the flash or the BGV and basically loaded up the flash tank enough where it kept the medium temp running. It put enough load on the medium temp, and it was actually able to build some discharge pressure and stay up. It wasn't the greatest discharge pressure, but it was enough to keep the rack running. And it was like minus 10 outside with like 30-mile-an-hour wind. So it was enough to keep the rack running. I mean, is that something that I know like most of the controllers don't have the ability. We don't have the ability to write to the set points like we need to. I mean, is that something that could be advantageous? You know, actually like increasing the flash gas pressure, you know, just under the maybe like 30, 40 pounds under the relief setting, just to load that thing up in the middle of the winter. Say like, okay, it's 0 degrees outside. We need to juice this, the flash tank up, a higher pressure to keep the system running and keep the medium temp loaded up.
Yeah, it's something that we've come across before that does help. Playing with floating your how can I say it, your receiver tank. It definitely do help, because it's right. You are correct with what you're saying. Is you need to keep load back on that system. So that is, in all honesty, like sometimes the best way that we have seen sometimes to do it is to really force your system to actually just run at a slight higher discharge pressure. Like I said, if you can't switch off fans and you can't stop airflow over your gas cooler, it's a struggle to do that. So if you can bypass that, especially for heat reclaim purposes, or you can modulate your flow through your gas cooler, you can force your discharge pressure up slightly higher. Because the problem is everything is just so low, there's not enough for the system to do, and it goes into funny season. So it sounds like the opposite of what you want to achieve, but if you're so low, you still want to run. You're not going to lose efficiency of a system, because you're pushing the discharge pressure up a little bit higher than what you think it should be, because you're still running fairly low. I mean, the energy saving when you're operating at a 59F condensing temperature is very good. You're not going to beat it by going to a 65 or something like that.
When you're bypassing the gas cooler, are you running? So if I was doing it, this would be my thought. I'd either do it off of both ambient temperature as well as pressure. So basically, if the pressure got low enough, basically we start bypassing, as well as if the ambient is low enough. And I'm assuming that it's a modulating thing all the time, right? It's not totally shutting off and totally bypassing. It's a modulating thing, right? Because then that way you can kind of meter how much refrigerant, because it's going to go the path of least resistance, right? What has more resistance, going through the gas cooler or going strictly in the flash tank? I do think flash tank, right? So it would be easier to go through there. So like that doesn't 100% close, right? You're just basically trying to modulate it to meter that temperature a little bit, just to keep that pressure up. Is that what you're doing?
Yeah, you will have to modulate it. I would rather go probably on all. I would rather look at all temperature-based ambient and gas cooler outlet. The reason why you're gonna have a system that hunts if you modulate on pressure, and the main reason is you need to remember there's a high pressure valve. And that high pressure valve that's the other problem that you get, is that high pressure valve is doing everything it can to keep that pressure at above its minimum set point. So it is choking the shit out of that system and trying to keep that pressure up, which again just make you gather so much CO2 in your gas cooler. So I mean, your low ambient problem that you have sometimes is just all your liquid and everything that you have just migrates out of your receiver straight and go and sits in your gas cooler, because again, oversized gas cooler leads to carrying too much CO2 when it's in the winter condition, and your high pressure valve is actually supporting that, because it's trying to choke that flow coming back to keep the pressure up. So if you're going to control on pressure and ambient temperature, like you're going to kind of start hunting and fighting each other.
So the second part of this, okay, like this low ambient strategy that we've kind of messing with. So everything up here in the U.S., every manufacturer has been controlling drop leg, the fans off of drop leg temperature. They go off of drop leg temperature. Now, we started to talk about this AHR. Why not use saturated condensing temperature? Use drop leg pressure and just convert it to saturation to drive the fans. And when you get to 87 degrees, where you're not going to start condensing anymore, you're running transcritical, just run the fans full bar. With us, I could see if you were somewhere warm using drop leg temp, but with us being in Chicago, when it goes from 50 degrees down to like 20 in less than like 4 hours, in when the sun goes down, I mean, it just hunts all over the place when it's cold. The fan comes on for like a split second, and that drop leg temp just shoots right back down. And then the BG or the HPV valve and the fans are just fighting each other, because the HPV valve's backing up gas, and we're getting real subcooled. And then we have subcooled liquid in there. Then the fans drop off, and then the pressure comes up. It opens up. It starts to get warm again, and then the fans just shoot back on. It's just like this constant struggle of like terrible control.
But can't you increase the band of that? I mean, I would say you must just look at increasing the band, because if you got your EC fans on your gas coolers, it's not an on and off situation. You start controlling. If you've got 59F as your minimum set point, for argument's sake, you want to start reducing that fan speed anything around 65F, and then that will give you that control to keep it there. Not to, because I hear you, if it's an on-off situation, you're going to overshoot the whole time. That's another thing with CO2, it reacts so fast. So you need to really modulate things. You need to keep things as steady as possible.
See, with like the whole thing with that is we're so cold outside with ambient, and say we got a 4-fan gas cooler. I mean, and of course, all these manufacturers are staging all the fans at the same time, which I wholeheartedly disagree with. So they're staging the fans all on at once. So they start out, say the minimum speed's 10%. So those EC fans come on at 10%. You have 4 fans moving. You're basically have an entire fan would be running almost 100%, but between the 4 of them, it's just so much air volume that at that temperature, it just instantly shoots down before the controller could even react to the PID change.
That's where the bypass would come in, right? Because then you don't have to worry about that. Like, I see what you're saying, because like I think even if you would bring on 1 fan, Kev, it would be too much. Like I'd think it would just be too much, because the theory is every single time you go half the temperature outside than what the thing is rated for, basically, am I right? It's gonna double in capacity, right? For all intents and purposes. So if you have a condenser that's rated for 100,000 BTUs at 120 degrees, and you basically make it 60 degrees outside, that condenser fully loaded would be rated for almost 200,000 BTUs. Would that be correct?
Yeah, not just that. The problem is when you have those low ambient conditions, your load inside the store would not be 100,000 BTUs. It would be only 20,000. So it's that the gap stretches so far away. That's why I said, like, I've literally seen where the system can bypass up to 90% of that gas cooler, even 100% of that gas cooler, and basically still operate. There's still so much there because the load is so little. Like it really can handle it. So I mean, the other thing is, like, it depends if I don't know if there's any store heating or something like that, because that's something else that goes with this. If you do bypass the gas cooler, and you obviously basically turn your condensing around the heat reclaim side of life, that helps making control better. But it's not a given that there's always, if there's no store heating. I mean, if there is store heating under those conditions, you will have a constant load, and you basically can actually run and condense your system without making use of the gas cooler at all, and just doing the heat reclaim side of life. But if it's not there, then yeah, you will have to modulate the flow going through your gas cooler.
So is there any downside or like negative to controlling it off of droplet pressure instead of temperature? Is there any like where it would be negatively impact the system?
No, I don't think so. I can't say particularly. I think the problem that you are describing here is more, like we said, a capacity and condenser size point of view. That, yeah, even whether you control or whether you drop or whether you on off, if anything is running, then that's why I say, I think even if you switch everything off, if there's a slight breeze or something going over that condenser, you're still over condensing. You're still making it hard for you. The problem is you're making it hard for your system to maintain above its minimum set point.
So I have a question on this. I know Emerson right now is in the plans of making some of their set points configurable and writable. So like you could basically take, if the ambient gets down too low, you could basically, instead of relying on the subcooling to be set for 5 degrees during subcritical mode, right? You could basically have a deciding factor to change that down to, let's just say, 3 degrees. So if you're only doing 3 degrees there, you're going to have that flashing off anyway outside of the HPV. And then because now you're not choking down so much because it's not trying to control 5 degrees of subcooling, it's now going to control 3. Your BGV will actually open up more, and then basically then transfer that energy over to the medium temp compressor. Is there any downside to having that do that? Because I've seen some of the older racks used to be only be set for 3 degrees. Now they seem to be doing like 5 degrees, and I've seen some customers were like, yeah, we're going to jack it up to 10 degrees of subcool, but then that just it feeds down, it clamps down on the HPV too much. So by changing that subcooling set point, is there any kind of bad things that might happen by doing that?
No, I don't think there's anything bad that will happen with it. I think it's good that suppliers are opening up more flexibility to the user at the end of the day. I mean, every application is different. That's sometimes the biggest problem you have is there's not that much flexibility to optimize and allow yourself from a control point of view to do what you want to do or to mitigate issues that you have. So no, I don't think there's an issue. Like I said, I think the subcooling set point on the gas cooler outlet, just yes, it will drive over condensing in a low ambient condition. So if you can have the ability to set it higher if you are in a very cold area or region or operating mode, definitely will make a difference in the overall control of the system. Because yes, it's literally, I think the issue is the main issue you have is there's nothing to move around, and your system is just trying to keep within its limitations that you have set for it. But it's finding it hard to keep it there because you have, put it this way, it's the law of nature is fighting the high pressure valve. Like it's cold outside, there's some fans running, there's very little load, there's a lot of heat going out through that gas cooler. It's you've got a mechanical or electronic valve fighting the laws of nature, which is hard
Yeah,
for
it's
the
fulfilling
electronic valve.
what you want at the end of the day. You're getting a massive amount of subcooling from a little bit of fan running. I mean, it's a correlation of all those things. I mean, the pressure thing seems like the controller is able to handle a little better. The pressure doesn't tank as fast as the drop leg temp is what I see. So it gives the controller a little bit more time to smooth out the fan reaction on the pressure side, but the temperature, it just instantly, like you're talking like within a few seconds before the controller, most controllers could even update to even make a PID change. It's already in the tank. But I mean that's a whole system design issue. I mean most of these US designers, they're not no split. I mean I personally would love to see split with CO2. I mean, I'm sure you guys have it like up in Europe, but like out here, like we need it. I mean, it's so cold here most of the time. Though our condensers are just, the gas coolers are just massive.
I don't know if you could do it because I mean, unless it's a separate chambered, gas cooler, right? Because like a lot of the abatics that you see basically, don't have a divider right in the middle. So if you pull off the one side, you're going to be pulling, less air across, but you're still going to be over condensing. I mean, I had to think, unless you would be able to control, you'd have to use relays to shut off each individual fan to make it more productive, right?
I mean, that's one way to do it. We don't have very many adiabatic. Like we have fewer. We have, most of ours are just standard gas coolers.
Okay.
Yeah, I mean that also won't help you in the windy cold conditions. At least the adiabatic is some buffer to the wind. So an open coil is, that's gonna pull the wind towards it.